But I'd like to, Winchell could comment more on that sometime if you're interested. I'd like now to open this GIS and PA environment. And as I noted, this is a common thing in many of my boot camps when we have an all-day thing for GIS. And this one was actually created in Melbourne. And what we did here is we incorporated convenience stores and supermarkets, and did that in exactly the same way because we were operating with PLE limitations. And so here are, the Westgate supermarkets, and oddly enough, one called Meerkats, and they even have 7-Elevens there, which is interesting, but Kohl's, etc. A whole bunch of Kohl's. These are, I think, yeah, these are these these are supermarkets? Kohl's is, okay, yeah, it's a supermarket. So in any case, we did a very similar thing, but then we further incorporated parks and mapped out parks within Melbourne, which is a city recommended by many parks, many beautiful parks, and we mapped down the locations of parks. That's what these green spaces are. I went running in some of the parks in the city. And more to the point, though, we elaborated this model. You'll recognize this basic state chart. I mean, I've adapted it here. But in transit to home, heading to supermarket, shopping in supermarket, basically similar sort of thing. But what's been changed is we've endogenized a lot more factors, ladies and gentlemen. So instead of just flipping a coin and deciding which one we go to based on preferences alone, we look at this probability of shopping wisely, was what it was called. And probability of shopping wisely takes into account this, the distance to the supermarkets, as well as the preferences, okay? And the basic idea is that if you really, so you prefer in general shorter distance to a longer distance, but if you really want to go to a supermarket, the distance to it will be sort of correspondingly lessened, okay? So the idea is that, if you have a really strong preference for convenience store food, for example, the psychological distance to a convenience store will seem smaller. If you have a really strong preference for convenience store meals, for example, the distance to the supermarket will be correspondingly distended. And then I sort of took the weighted, the fraction of one compared to the sum of the two. And I used that to determine a probability. Now, this rule could be faulted. I came up with this rule quickly, and it wasn't terribly deep. But the point is, we could take into account distance. And this makes all the difference. Because if we think about food deserts, and we think about the impact of having to go further, the residents in west side of Saskatoon who live in a food desert now, unfortunately, they can go to Giant Tiger on the north side of the city, but it's inconvenient, right? They have to take 2 buses to get there, and it's expensive. It takes a long time, and what are they going to do with the kids while they're away in this way? It's a big issue in their decision making about where to shop for food. And so that factored in a big way into this decision here. What also factored in is their preferences, to be sure. Now, in this case, we could have had their preferences be shaped by the preferences around them, and we would have had further neighborhood effects. But what we did is we expanded it in other ways. And this is all during the boot camp, of course, during less than a day. So we had a further attempt to incorporate the fact that that your decision about where to go is shaped, and how frequently to go shopping is also shaped by how much food you get at both. So you go to supermarket, maybe one trip you make every 2 weeks, you can get, a week and a half of food. you may be able to actually forestall many other potential shopping trips because of it. So you don't want to just consider, well, what fraction of the time do you go to a supermarket or convenience store? Maybe you go to a convenience store half the time, but in the time you go to a supermarket, you buy a lot of food. And so you are sustained nutritionally by that food for a longer time. So if we want to understand the impact of food procurement choices on people's health, we can't just ask about the fraction of time they go to different supermarkets or convenience stores. We need to reason about how much they get. And so because of that, we actually had an endogenized representation of their larder, how much they buy. And so we had count convenience store meals remaining, count supermarket meals remaining. And the idea is that, you purchase some food and you're eating the food. Maybe at any one time you have a mix of food in there, but at some point you run out of supermarket food, and then you might go to grocery food. You might do a couple dashes to the convenience store for short shopping, but then you might go to the grocery store, really load up, and then you're sustained for a while from that. And so this was this kind of logic diagram. And you'll notice this is all supported in any logic. It's a nice illustration of what you can do to create a fairly transparent model that can be understood. We had a decision process for eating meals, and this is the sort of thing we can show to stakeholders, right? Do we have both types of food to choose from? If so, flip a coin according to your preference, about whether to eat one or the other. If not, do we have only convenience store food? If so, eat a convenience store meal. If we don't have only convenience store, it means we have grocery store. Do we have supermarket for only? Yes. Otherwise, if we have no food, go shopping. Okay, this is a process. Now, behind this, ladies and gentlemen, is actually code. So this hides the code, but if you were to go look here, behind this, do we have both types? There's actually a condition. This is the condition in Java. What this is saying is the count of convenience store meals that we have greater than 0, and that's what this means logically, and is the amount of supermarket meals remaining greater than 0. If so, then true, we go to this, otherwise that. So this encodes, each of these blocks encodes some logic, but it encodes in a logic that's clear. Here's eat a convenience store meal, and we wrote it like this. Count convenience store meals equals this one minus 1. Now it turns out there's a much more compact and beautiful way to write that, but I just want to show it. Energy intake, the sort of the amount of energy we've taken in corresponds to a convenience store meal, and the count of convenience store meals eaten is incremented. We're recording over time how many meals I've eaten from a convenience store or from a grocery store. Okay? Now, that's not the end of the story, because this energy intake here, whether from a convenience store meal or a grocery meal, they're different, and they end up affecting my energy in an energy balance equation, where my weight, and this is very simplistic, but it gives a nod to some extremely well described, characterized, calibrated models, particularly out at the NIH, where Kevin Hall's work, an intramural researcher, he's done exquisite modeling of energy metabolism and how weight depends on energy intake and energy expenditures. And there's nonlinear relationships and feedbacks involved. Kevin Hall, Hall, and I'm pleased to say that he's a Canuck. Anyway, he's really an extraordinary researcher, and he's done all these studies with people. They put them in these special chambers where all the gases that they breathe in and out are measured, and they feed them very controlled meals, and they measure how much they exercise, and they examine their basal metabolic rate, and they basically evolved some exquisitely well-calibrated models of human body weight and composition change and metabolism. And then you can tie those in to epidemiological models. And so this is type of work I've done, Ross Hammond has done at Brookings. And basically this is a crude sort of nod to that, where we have weight in kilograms, we have some energy expenditure that goes on proportional to my weight, rate of energy expenditure. We have some from physical activity, some from basal metabolism, and then we have some energy intake from food. And this shapes my weight state. So what I'm trying to say is here, now we have a set of causal pathways being delineated from, the location of food resources to behavior in terms of decision making for what to eat day to day, in terms of food procurement, where I go for food, which ripples through then to affect my energy intake, which affects my weight and my weight evolution over time. This is all within the scope of a boot camp model. This is a bit less than 1 day of work. Now, obviously, things here would need to be pinned down, but there's published models. Kevin All has published several models, and I could give references where he's related the equations, and I actually have the models.
Did Finlay or whatever her name is get into this type of stuff with their work?
I'm not familiar with her working in the same area.
No, I'm trying to think where we first met through that.
Yeah. You're talking about Diane Feingood.
That's it. Yeah.
Diane Feingood. No, she didn't really get into. I wanted a student of hers to go in this direction, but it didn't happen. Okay. So it was a promising prize, and the student decided they weren't interested. So fine. I've got another student who's worked on it since. In any case, this evolution of weight is endogenized. And it depends on food consumption. So here we have our Melbourne example, and let's see if this can refresh. It's getting data on Melbourne here, and here we have people moving around, and over time, they're obviously these grocery stores and convenience stores are placed via a very similar thing that we did randomly. We obviously could load these in, not randomly. They're placed via the locations we found in the GIS database. The homes are random. And over time, these individuals' weight will evolve. And the weight will evolve. As the weight evolves, guess what else evolves? What else evolves is this. Their body size. So you'll notice that their girth here is made dependent. Their radius x is made dependent on their weight in kilograms, and so they're moving. And ones that have, notice there's a difference here. This one is gaining a bit of weight. This one is losing.
Some of them are kind of losing or something.
Yeah, it's not quite cachexic, but it is. Oh my gosh, there was okay, too many floaters there. In any case, the point is that we've endogenized this, and this actually depends on locations and their physical activity. I should have noted their physical activity depends on parks and how many parks are nearby. And we actually modified this so that, and I don't know that my version of it right here includes this, but we could add grocery stores interactively. This, again, is in the course of the day, so we could add a new grocery store at a point of our choosing and see how it then affects weight status for that neighborhood. Now, so we've endogenized food getting, depending on distance and preferences. Had it ripple through to weight, we could have weight norms further affect target weight and so on, although that wasn't captured in the model. But within a model like this, you can then have outputs of various sorts. And we'll be exploring outputs this afternoon. But if we go up to Maine, for example, we go down Maine and take a look at, here's our map in Maine. The same sort of thing. But now we can have maps here. I should do it in the running model here. Here's scatter plots. Each of these dots is a person, a fraction of meals that they've eaten at a convenience store versus their weight in kilograms, for example. Let me go up. Here's for people the grocery store distance from them versus their weight in kilograms. The grocery store distance ratio, or convenience store ratio, how far is a supermarket compared to a convenience store, and how does that relate to their weight? We could look at these associations which emerge from this model. And we could compare these associations to any associations that might have measured for a population. Here's distance from a park to weight. Okay, the further you are from a park, the higher your weight tends to be as a general rule. These are the sort of statistics you might get out of a model. These statistics could be compared against any comparable empirical data. And this afternoon, as time allows, I may discuss some studies that we're doing that can collect exactly the sort of information using smartphones to collect information on people's food or collect automatically information when they weigh themselves, etc. But we can also use help think through what measures would be good if we were to partner, with researchers in this area. Maybe it would be, Scott Leatherdale and his study, of teenagers in school populations, or maybe Mark Tremblay's group with CHIO. We were to partner with them, on a population-based study. What sort of measures, what sort of metrics might we collect from the population that could show interesting relationships? And a model like this, while not a perfect representation of the world, no model ever is, it might stimulate thinking and help us think through more clearly and more reliably our sense of what metrics would be more reliable, which would be less. It might help highlight to us certain metrics which would surprise us by not being reliable and highlight others which seem more interesting. So the point is, given a model like this, which shows a synthetic population, we can readily, because we have kind of this God's eye view of the world, we can collect all sorts of information from here. And by showing different sorts of information, we can advance our thinking about lines of evidence that might be useful from the real world, and where they're available, compare them and improve our model. So this is an example of a model. It's still a toy model. This is a model built in a boot camp. But I think the general idea behind it, the idea that we can endogenize decision-making involving food seeking, that we can show within a model that the impact of that on weight evolution, that we could have neighborhood structure and availability of parks ripple through to affect physical activity. There's a solid idea there. It's not pie in the sky. It can be done. And it can be done in ways that link in with the type of big data that we're increasingly collecting and that our research program is really increasingly centered around, coupling that with models. So this model that we started this morning, simple though it is, laid the basic mechanisms that, within an afternoon could be expanded to the sort of things that we see here. And I think you could see between these state charts and between these action charts, as they're called in AnyLogic, they're accessible via this mechanism here, and via these stocks and flows. You can actually have, despite the conceptual textured character of what we have here, you can actually have a model that you could show to someone and explain without them being turned off like they would be by page after page of code. So this model, a lot of moving parts, a lot of pieces, and a finicky GIS system, but it is doable, and this is about a day's work. You can imagine what would happen if you had 6 months or a year to develop a model like this. Okay? So those are some comments. Any questions or points for discussion about this GIS functionality? I happen to believe it's a really exciting aspect of AnyLogic, particularly for population health researchers. How the plots get generated? So we're going to be talking some about plots this afternoon and producing some. These plots are very easy to produce. Do you remember in the past few days, Carolina, we put in like pie charts and we put in time plots? Do you remember that? These plots here are populated in a way that's a little bit more demanding via that than that. Whoa. Okay, sorry, I didn't mean to do that. But not too much so. And we're going to see how we could put in place these plots in the form of histograms, in the form of these scatter plots today. Basically, you define what's called a data set, and this plot just plots out a data set. In this data set, meals eaten and weight data set, that's for our scatter plot, where each person might be a person. Each dot might be a person, right? And let's go over here, and let's go check it out. So this is in Maine, and analysis data. Here's the meals eaten and weight data set. And here, we actually aren't defining directly in it, but instead there's an event which updates this. So periodically, every 1 month, we clear out all information from here, and we then go through each person in the population. That's what this does. It obtains information from them, like for this person, what's the distance to the nearest supermarket? Remember, we put in some code like that. And then we take that and we'll add it in, for example, these attributes. So this distance to nearest supermarket, here's distance to nearest supermarket, and here's the person's weight in kilograms. So that would go into the plot, into the data set that's plotted the relationship between distance to nearest supermarket and weight in kilograms, and vice versa. So it's a little bit of code, but all this code does is it fills in values to be plotted in these data sets, okay? So all it does is say, hey, this is one data point. This is the X, this is the Y. Or, yeah, I think that's right, the X and Y successively, yeah. And then, so this is kind of the outcome variable, and this is the covariate of interest. And then the plot takes care of automatically plotting this data set. Is that helpful? Yeah. Well, you do have to put this code in, and this afternoon you'll be coding up a little bit like this. It looks a bit large here, but that's just because I'm doing a bunch of plots at once. There's this data set, and there's this data set, and this one, and this one, and this one. So I'm doing something like 5 data sets at once, and that's why there's a bit of mechanism here. But for one data set, it's not too bad. Okay? Any other questions about that? Those sort of plots, those scatter plots, are just wonderful for visualizing what's going on in a model. You have each person be a dot there, and you have one, bivariate scatter plots of various sorts that plot out the relationship between attributes of that person and health outcomes or whatever. They're really helpful for understanding what's going on. Okay? Questions?
Yeah.
Yeah.
I would appreciate it if we could practice use GIS for mapping, for example, diabetes prevalence in Canada, different countries.
Okay.
So we could practice this. Use.
Yeah, you could. You could map it out with this, absolutely, in the sense that you could overlay on the map, an indication of prevalence recorded for that area. What you would need to couple it with, the GIS databases used here, they wouldn't have data built into them of GIS prevalence, of the diabetes prevalence. So you would need a corresponding database which told you, for this region of Canada, say for this health region, what the prevalence was, or for this geographical area. And you would need to map that to geographically meaningful quantities. Like this GIS database doesn't automatically know where the health regions of Saskatchewan are. And so what you could do, and we have done things like this, is using what are called shape files in GIS. You could tell it what the health regions are, and then you could read from the database of prevalence in the health regions and plot out colored plots accordingly. In fact, the very first version of this model, I have to give credit to my student Dylan Knowles, and he has a model, and I think I provided it to you here, but it's called Saskatoon Food Environment or something like that. And that model, maybe it's under the hybrid model area. GIS food environment. Okay, I may have taken it out. In any case, what it includes is a map over space of the prevalence of overweight and obesity for that area, and that's layered atop this illustration. But his depiction of weight evolution was oh, here it is, SKGIS food environment. It's in my examples. And so if you were to load this one is more fanciful, shall we say, in its depiction. He doesn't have as much experience with system dynamics modeling, and so he wrote kind of a feedbackless weight change. So here we have Dylan's version of this model, and here you just have energy out at a fixed level. And as a result, without this regulatory process operating on weight, what you see is a situation where people's weight gains tends to be fairly unrestricted, and so you'll have distended representations coming. But the important thing here, and this relates to your question, is he has mapped out prevalence of obesity. You could see these individuals are in fact, this is awkwardly in the presence of the university. So
Well, yeah, there's a lot of fast food.
yeah, that's true. Okay, so unfortunately, the university is being highlighted as a concern. But this is mapping out the prevalence of obesity in different areas according to geography, using this this heat map type thing, which characterizes it. And it turns out it's super easy to do on any logic. You just say plot this quantity, the maximum value is such and such, and map it from this color to that color. Closer it gets to the end, it gets closer to a certain one of the colors, and so this is mapping out the burden of overweight at certain areas. Yeah. So yeah. So what it lacks in realism, it has advanced in imagination. Yeah, indeed. So I won't challenge your imagination by going further, but this is a model which laid the groundwork for more serious thinking about it. But of course, the truth of the matter is there are good published models on weight change that literally we could substitute in here. You could just substitute them right into the model, paste them right in there. They'd be rich, empirically grounded, highly calibrated and tested models from the NIH, from these food lab studies that we could place in, hitch it up to physical activity, hitch it up to assumptions about food-going behavior and consumption, hitch that up to the type of food-getting behaviors that we just saw, and have a model. And then we could refine our analysis of how people make decisions. What are their decision-making based on? How would the presence of a bus route along a certain corridor, which could take them to areas with grocery stores, how would that affect things? How would the availability of parks, how would the availability of community-owned grocery stores in this area of the city, how would that ripple through to weight? The basic ideas are solid, and unrealistic depictions in Dylan's original model behind it had the seeds of greatness in it. And this maps out the burden of obesity in a way just similar to what you were talking about, in a way that can be quite nice for parsing what's going on. Okay? So we're going to talk more this afternoon about output mechanisms, and critically, ladies and gentlemen, you do only a certain amount of analysis in any logic. For us, we export it then to other packages like R, and do major analysis in these other tools. Tools which are fit for purpose for the statistical analysis, for the preparation of sophisticated graphs and visual analytics beyond what AnyLogic provides. AnyLogic is not a tool for all of the research process, but it's a tool that fits in one place, and then we couple it with other tools. And if there were interest, Winchell could actually show you an export tool that automatically exports things from AnyLogic models to R. Yes, Ron.
That's what I was going to ask about,
Yeah.
because the last time you were starting up this
Yeah.
incredible stuff, so you've already, Winchell's taken this a lot further.
Winchell has put in place these mechanisms for outputting. And this afternoon, we will see how do you get data out of this model and into other forms, including forms that could be read in by R, comma separated variable files, that sort of stuff, and into commonly used tools like Excel, which could allow you to directly see what's being put in there. I'll also give a nod to how you could draw data in from those tools or from databases, because you might draw a parameter assumptions, not from the from the experiment definition itself, not just from the user interface. Maybe you want to draw it from a database or from an Excel file, and you can do that very readily too. Okay, so that's for this afternoon. That'll be after lunch. Should we come back in an hour?
Sure.
Okay.
Downstairs to whatever the room was.
Oh, what should we do with our things then?
Ooh.
We gotta take them with it, because somebody may have this room reserved. So
I see. And we can't put them in that lower room
we
right
should
now.
be able to.
We
Now?
Maybe, maybe not. It depends on when our colleagues from our direct division are at
Okay.
their meeting.